Aluminum is like the superhero of metal, as flexible as a contortionist and tough as a tank. But have you ever pondered how this mighty metal morphs from a solid block to a whisper-thin sheet of foil? Let's unravel the mystery together on how millions of pounds of aluminum is manufactured to make this extremely thin sheet of foil we use every day from our kitchen cabinets. Back in 1911, a Swiss company came up with a nifty invention: aluminum foil. Surprisingly, it wasn't meant for cooking at first, but for wrapping their famous Toblerone candy. Fast forward, and this shiny marvel found its place in kitchens worldwide. Why? Because aluminum boasts a superpower. It's an ace at blocking out light, heat, and moisture, making it a must-have for preserving freshness in your favorite foods. Before the 18th century, numerous scientists embarked on a quest to unlock the secrets of aluminum. But alas, their efforts were futile. The extraction process proved to be a formidable challenge. Then, a breakthrough. Someone cracked a code, but all they could muster was a mere speck of aluminum powder. Talk about scarcity. Pure aluminum became the holy grail, its extraction process shrouded in complexity, making it even more precious than the coveted gold itself. Picture this. The game-changing moment in aluminum production arrived with the groundbreaking discovery of electrolytic reduction. But hold your horses. Let's rewind to where it all began. Meet bauxite, the unsung hero and primary ingredient in the aluminum production process. This mineral is packed with aluminum oxide, the key to unlocking aluminum's potential. While clay also holds aluminum, bauxite steals the spotlight for its cost-effectiveness and swift accessibility, making it the go-to choice for aluminum production. Entering into the world of bauxite, which is found in vast open-pit mines stretching across tropical regions, where bauxite is unearthed and transported to refineries for the next phase of its manufacturing process. Among these mining giants sits the impressive Alcoa mine in Australia, churning out a staggering 30 million tons of bauxite annually. We start with the refining process. It all begins with crushing the bauxite ore into a fine powder before it undergoes a transformational fusion with caustic soda in a grinding mill. The result, a slurry teeming with ultra-fine ore particles, ready to embark on the next stage. It enters the digester, a high-pressure vessel that is like a steam-powered pressure cooker. Here, the slurry is subjected to intense heat, reaching temperatures between 230 to 520 degrees Fahrenheit, 110 to 270 degrees Celsius, and pressure levels of 50 pounds per square inch, 340 kPa. This controlled chaos lasts for a duration ranging from 13 minutes to several hours, ensuring that every ounce of aluminum-containing compounds is meticulously dissolved. Additional doses of caustic soda may be introduced if the bauxite has not been thoroughly mixed. The sodium aluminate solution, now a scorching slurry, undergoes a journey through a series of flash tanks designed to decrease pressure and recover heat, which is then repurposed within the refining process. From there, the slurry is directed into a settling tank, where a fascinating phenomenon unfolds. As the slurry settles, impurities that resist dissolution in caustic soda gradually descend to the tank's base. This residue, affectionately known as red mud, comprises fine sand, iron oxide, and traces of titanium oxide. Once the impurities have settled, their residual liquid, resembling a robust cup of coffee, flows through a network of cloth filters. These filters diligently capture any lingering particles of impurities, while the recovered aluminate and caustic soda undergo a thorough wash for potential reuse. The filtered liquid then continues on its next adventure, coursing through a series of towering precipitation tanks. Within these monumental tanks, a mesmerizing dance takes place as alumina hydrate crystals, along with alumina bonded to water molecules, are introduced from above. These crystals act as nuclei, attracting dissolved alumina, which then precipitates and settles. After a thorough rinse, the crystals journey to a kiln for calcination, a process involving intense heat to liberate the chemically bonded water molecules from the alumina molecules. As the crystals traverse the kiln via rotating cylindrical conveyor, temperatures soar to a blistering 2,000 degrees Fahrenheit, 1,100 degrees Celsius, driving off the water molecules and leaving behind pristine, anhydrous aluminum crystals. Exiting the kiln, the crystals make a pit stop at a cooler, where they undergo final processing to yield pure aluminum. liberating the bond between aluminum and oxygen within aluminum. The process of smelting involves breaking the bond between aluminum oxide molecules by electronically reducing alumina into aluminum metal. This intricate dance unfolds within a steel V18 known as a reduction pot. At the base of the pot lies a lining of carbon, which serves as one electrode conductor in the electric current system. Suspended above the pot are carbon rods, forming the opposite electrode. These rods hover about 1.5 inches, 3.8 centimeters, above the surface of the molten aluminum, which accumulates at the pot's floor. Reduction pots are meticulously arranged in rows, forming pot lines where 50 to 200 pots are interconnected to create an electric circuit. Each pot line boasts an impressive annual production capacity, ranging from 66,000 to 110,000 tons, 60,000 to 100,000 metric tons of aluminum within the reduction pot. Aluminum crystals dissolve into molten cryolite at scorching temperatures of 1760 to 1780 degrees Fahrenheit, 960 to 970 degrees Celsius, creating an electrolyte solution that facilitates electricity transmission from the carbon rods to the carbon line bed. An electric current courses through the cryolite, prompting a crust to form over the molten aluminum surface. Periodic stirring introduces additional alumina into the mix, breaking and incorporating the crust. As alumina dissolves, it undergoes electrolytic decomposition, yielding a layer of pure molten aluminum at the bottom of the smelting cell. Meanwhile, released oxygen molecules gravitate towards the carbon rods, eventually escaping in the form of carbon dioxide. In its molten state, the refined aluminum is carefully extracted from the smelting cells, transferred into crucibles, and then poured into furnaces. Here, additional elements can be introduced to create aluminum alloys tailored to specific end product requirements. While foil typically consists of 99.8% or 99.9% pure aluminum, other compositions can be achieved at this stage. The molten aluminum is then directed into direct chill casting devices, where it undergoes controlled cooling to form large slabs known as ingots or roll stock. Once cast, these aluminum ingots undergo a series of mechanical processes to transform them into aluminum sheets. Initially, the ingots are heated before being fed through a series of rolling mills, gradually reducing their thickness. This process, known as hot rolling, can be repeated as needed to achieve the desired thickness and properties. Following hot rolling, the aluminum sheet undergoes cold rolling, wherein it is passed through rollers at room temperature to further refine its thickness and surface finish. This meticulous process ensures that the aluminum sheets meet the stringent quality standards required for various applications. Cold rolling not only refines the thickness and surface finish of the aluminum sheet, but also enhances its tensile strength and hardness. During the cold rolling process, the aluminum sheet may undergo annealing between passes. This crucial step involves heating the sheet to soften it and enhance its formability, while also alleviating stress accumulated during cold rolling. Upon completion of cold rolling, the aluminum sheet is primed for the specialized process of transforming it into aluminum foil. The foil rolling process is a meticulous endeavor, focusing on precision to attain the desired thickness, surface finish, and properties. Cold-rolled sheets are meticulously guided through a series of specialized foil rolling mills, each meticulously designed for crafting thin aluminum foil. These mills boast multiple rolls that gradually reduce the sheet's thickness, ensuring uniformity and a smooth surface finish. To further refine the foil, tension leveling may be employed, gently stretching it over a series of rolls. Throughout the rolling process, a thin layer of oil or lubricant is applied to the foil to minimize friction and prevent adherence to the rolls. Intermediate annealing may also be necessary to maintain the foil's ductility and facilitate additional thickness reduction. Once the desired thickness is achieved, the aluminum foil undergoes final annealing and finishing processes to enhance its properties and ensure consistent quality. Heat treatment in a controlled environment alleviates residual stresses, enhances flexibility, and optimizes mechanical properties. The wide foil sheet is then slowly cut into narrower rolls, standardizing commercial sizes for aluminum foil. It's important to note that stringent quality control measures are implemented throughout the production process. Rigorous checks are conducted to ensure the foil meets exact specifications regarding thickness, tensile strength, and surface finish, guaranteeing superior performance and reliability. The aluminum foil is wound onto large rolls and cut into standard-sized rolls or sheets to meet customer specifications. The finished foil is meticulously packaged and labeled for distribution to manufacturers, retailers, and other end users.